In this lecture, we're going to go over this notion of a complete measure. So here's the definition. A measure on a measurable space is called complete if the following happens. Suppose I have a set with measure 0. Then any subset of this measure 0 set n is going to be measurable. It's going to be inside this sigma algebra. Well, because of the monotonicity, we know that if E is a subset of some set with measure 0, then E is going to be measure 0 as well. So in other words, a measure is complete if for every set which has measure 0, its subset is first of all measurable, and when it's measurable, it also have measure 0. So let's take an example. So if you take the standard Lebesgue measure on the real line, then what you can show is that if you take the real line and the Lebesgue measurable sets, so this is, let's use L to denote the Lebesgue measurable sets, well then it's going to be complete, right? It's fairly standard fact about Lebesgue measure. But let's consider the following example. If you just consider the same real line and if you construct a parallel sigma algebra, all right, then you restrict the Lebesgue measure. Well, you know the Borel sigma algebra is a subset of all the Lebesgue measurable set. So you take your Lebesgue measure and you just restrict it on the Borel measurable sets. Then this is not going to be a complete. The reason is that in the real line, you can find some measure 0 set that's actually not Borel. I'm not going to show this fact. It's about the cardinality of the Borel set is smaller than the cardinality of the Lebesgue measurable set. So I'm not going to go over into too much detail, but as a fact, you know it's not going to be complete. So the goal of this lecture is the following. So even though I can have a measure that's not complete, I want to show that you can always extend it to a complete measure, of course, on a slightly larger sigma algebra. So here's the main theorem we're going to show. So here's the theorem. So suppose you have mu is a measure on some x and b. Usually I would say it's not complete, but it doesn't really matter. So suppose you just define the sigma algebra B bar to be the sigma algebra generated by B's, and also all those subsets of null set. So E, where E is contained in N for some mu of this N going to be 0. So if you consider all the subsets of mu null sets, and also you take everything inside the sigma algebra B, you get a collection of sets. And when you have a collection of sets, they are not sigma algebra, but you can always generate a sigma algebra, which is the smallest sigma algebra containing all of them. So on this set, I want to show the following. So then there is a unique complete measure. Let's call it completion. Let's use bar to denote the completion. So on the set x and b bar, where this mu bar is basically going to extend mu. So if you consider this mu bar and you just restrict it on the original sigma algebra B, then you will get mu back. Okay, so in other words, for every B inside the original sigma algebra, this mu bar of B has to agree with your original measure given under mu. So it's an extension of mu. So here is the main theorem we're going to show. All right, so let's divide the proof into several steps. So first of all, let's prove the following lemma. I need a slightly better explanation of this sigma algebra B bar. So sigma algebra generated by these sets is very difficult to describe. I need a better description. So here's one. So I want to claim, first of all, this B bar, what I can write it as all those unions of E and F, where E is coming from the sigma algebra B, and F is coming from a subset of a null set. So F is contained in N, where mu of N is 0. So F is something that may not be in B, but is inside a null set. All right, so I want to prove that. Well, to show that B bar, the sigma algebra generated by these elements is equal to this description, well, I basically need to show the right-hand side, first of all, is a sigma algebra. The right-hand side clearly contains all the B, and it contains all the subsets of null set. Okay, so I actually only need to show that this is a sigma algebra. Okay, so proof. Okay, so suffices to show the right-hand side is a sigma algebra. All right. So why is a sigma algebra? Well, let's show the need to verify to satisfy all the definition of a sigma algebra. So first of all, the empty set. Well, that's going to be inside the B bar. That's pretty clear. Nothing against this. All right. So now let's show that it's closed under taking complement. So suppose I have a E union F that's contained in B bar, a typical element where F is contained in some N where mu of this N is going to be 0. All right. So let's look at what is complement. So let's consider its complement. All right. So when you take the complement, okay, so let's draw a picture. So you have an E here, and you have some F, which is contained in a larger set, which is have measure 0, so that's N, and they're all inside this X. What is complement? You can show the following. So first of all, you can show that, well, its complement consists of, first of all, the complement of the E union N. So this part, this is the E union N. So X take away both E and N. Okay, so that's certainly one part. And I still need to take something else. I need to take away anything that's inside N, but not inside F or E. Okay, so I need to union everything that's inside N, but not in E nor F. Okay, so I can write it as a union of these two. Now, E and N are from the original sigma algebra B. So the union is again in B, and their complement is certainly in there. So this is an element inside B. And N is a set that's a null set under the original one. So this E take away the E union F, that's going to be a subset of a null set again. So this is contained in N, where mu of N is going to be 0. Well, a typical element on the right-hand side is a union of something that's in B, so this is this part, and something that's contained in a null set, which is the second part. So by definition, this is contained in the right-hand side. Okay, so we show it is closed under taking complement. And finally, I want to show that it's actually closed under taking countable union. So let's take EI union FI inside this B bar. And here, each of these Fi is going to be inside some null set. It can be different null sets. So let's say it's inside Ni, where mu of each Ni is going to be 0. It's going to be a null set. So mu of Ni is going to be 0. So now let's consider their countable union. This I going from 1 to infinity. So let's say I of these EI union FI. I'm taking a union of a bunch of things. So you can say, well, this is essentially the union of all the n's. Okay, somehow my I looks like n. So here's I going from 1 to infinity of these EI. And I can take the union of FIs. Okay, so I go from 1 to infinity. So now what do we have? Well, the first part again is a countable union of elements in B, so it's in B. Well, I want to show the second part is inside the null set. So let's consider the second part. So this infinite union of these Fi, that's going to be contained in the infinite union of these ni's. Well, now the question is this infinite union of ni a null set as well? Well, so what is measure I going from 1 to infinity to the union of these ni's? Well, even though these ni may not be disjoint, but we know by sigma subadditivity it's bounded above by the sum of their measures. So I going from 1 to infinity. Each of these ni is going to have measure 0, so we're taking an infinite sum of 0, so that's going to be 0. And we know the measure is non-negative and it's bounded above by 0, so this is going to be a null set. Okay, so we show that this one is contained inside this union of ni, where mu of this union of ni is going to be 0. So it gives the second half. So by our definition, this infinite union is inside the right-hand side. So this shows the right-hand side is a sigma algebra. So now we have a better description of the sigma algebra. So it basically consists of a union of two parts. One is from B and the other is a subset of null set.